Good day, grade 12. This is lesson 6 in our series on momentum of about 8 videos in total. But let's first mark the previous homework that you had to do with your previous lesson. This homework is extremely important, and I want to urge you, if you have not done it, please go and sit down and do the homework. You know, if you want to create really nice tummy muscles, it has no use for you to go and lie down and have somebody pull you up all the time. It's not going to develop muscles. You have to do the work yourself. And the same goes for physical science. Watching me doing the work is not going to give you developed cognitive functions. So I want to urge you, if you haven't done it, stop this video immediately and first go and do it. This video won't go away. You can watch it later. Please do yourself that favor. Remember, I told you, you are your own best teacher. Okay, so let's look at the first problem that we had. Sam, with a mass of 70 kilograms, fall on an airbag with a speed of 15 meters per second. It takes him 1.5 seconds to come to a complete standstill, and you have to calculate the change in momentum. So Sam is falling down, so let's choose down as positive. And now I have to make sure that I write down all my equations, or all the numbers that I fill in with the correct signs. So there's my equation that I write down, and I plug in the values. I know his initial velocity is 0. He has a final velocity of 15 meters per second going down, which is a positive number. So this minus over here, that is that one there. It has nothing to do with the direction that is negative. Okay, so if I plug in all these values, then I get a final velocity, or a final force that is acting on him, of minus 700 Newton. That negative sign I need to interpret as a direction. I chose downwards as positive, so this direction must be upwards. Okay, let's look at our next example. Jim has a slightly smaller mass than Sam. He also falls on a solid floor with a speed of 15 meters per second, but in his case, it takes him 0.1 second. He's not falling on an air cushion, so it takes him a much smaller time to decrease his speed from 15 to 0. So I choose again a direction downwards as positive, and I write down my equation, fill in all the values. But can you see, in this case, I get a much greater force, one of 9,750 Newton. I have a negative sign, which I need to interpret as a direction. So I know the final force is 9,750 Newtons upwards. Now, Sam had a greater mass. He had a mass of 70 kilograms. He fell with the same speed, but the force acting on Sam is much less, even though he was heavier. And what is the thing that makes the difference? Well, the mass is going to influence this number over here, but can you see, in order to calculate your final velocity, you're going to take this number and divide it by the time. The smaller the time is, the smaller this number that you are dividing it by, the greater the force is going to be. And that gives me the answer for the next question. Refer to the impulse momentum theorem and explain why airbags are used as a safety precaution during a motor vehicle accident. Okay, now the first thing that we know during an accident is you're going to go from whatever speed you have to 0 in a short time. So your change in momentum is going to be quite severe. That is one of the reasons why why you get these slogans that say speed kills. If your speed is less, then your change in momentum will be less, and that will definitely have an influence on the force that acts on you. But the main thing is that you don't know beforehand when you're going to make an accident. So at times it's very possible that your speed will be quite high before you make the accident. Okay, so what we are trying to do with the air cushion is actually to ensure that the time over which your momentum changes becomes longer. So the airbag resists your motion and slows you down over a longer time. So if delta t becomes a greater number, then f must become a smaller number. Let me plug in some values so that you understand. Let's say the change in momentum over here is 12. Okay, Then if the time over which this momentum change was 1, then you know 12 times 1 will give you 12. So then your force must be 12 Newton. But if this time, for instance, changed to 2, can you see immediately for this to still become 12, which is the change in momentum at the end, my force must become 6, so my force is going to decrease. And if this time increase even more, let's say it's become 3 seconds, can you see in order to get 12 3 times 4, then this force must actually decrease more and become 4. So the more your time increases, the more your force will decrease. So the airbag is just there to make sure that your time over which the momentum changes becomes longer. The exact same thing with your knees that's bending. When you fall down or when you jump and land, your momentum changes from whatever velocity you have to 0 in a very short time. What your knees are just doing is increasing that time. The change in momentum is directly proportional to the product of the force that is exerted on the object, so the force, at the time. So all that I'm saying here is F is equal to delta T, or F delta T is equal to change in momentum. Sorry for that. Okay, bending your knees, you extend the time over which this force changes. Okay, so therefore the force that is going to act on you is going to become less, and therefore the chances of you hurting yourself will also become less. The next concept that we're going to look at is the conservation of linear momentum. Now here I have a situation of 2 people each with a ball, or each with a mass of some kind, and then there's a collision between them, and then each of them have a momentum afterwards. So you see the girl and the boy has momentum before, and then a collision occurs, and then they have a momentum afterwards. Okay. Before we get into the principle of conservation of momentum, I'm going to use Newton's third law to show you that I'm not lying when I tell you momentum is being conserved, that I can perfectly prove this from a law that you know is true. Okay, so let's look at this situation, the boy and the girl. You know that when they are in contact, each of them exert a force on the other, and according to Newton's third law, the force that A exerts on B is equal to the force that B exerts on A, but in opposite direction, and that's why I have that negative sign. I also know that the time that B is touching A is exactly the same as the time that A is touching B. So if I take my Newton's third law, that equation, and I times both sides by the time it takes for them to have contact, I end up with this equation. Can you see? I times both sides by the same number. But you know F delta T is equal to impulse. So the impulse on A is equal to minus the impulse on B. And what do we know about impulse? Impulse is same as the change in momentum. So if I have the impulse on A is going to be equal to the change in momentum of A, which must be equal to the change in momentum, or minus the negative of the change in momentum of B. This equation I can expand further to give me change in momentum as final minus initial. And of A is equal to minus the final minus initial of B. So let's just quickly take care of that negative sign and simplify that in front of the bracket so that I get minus B plus A. I'm now slightly going to change this equation so that all the final velocities are on one side and all the initial velocities are on the other side. I think some of your teachers will say, take this. I don't like the wording on this. Mathematically, to me, it's a bit, Afrikaans word is grillerig. It's not nice. But anyway, some of your teachers will say, take it over the sign and then it becomes positive. I prefer to say, add to both sides MAVA, and then these two will cancel and I will end up with a plus MAVA on this side. However you formulate that, if you have all your initials on this side and all your finals on that side, your equation will change to this. If you struggle to get from this equation to that one, just pause the video and quickly do it on paper for yourself. It should become quite clear. If not, do ask your teacher. Okay, so now we see if I have my momentum, if I have all the final momentums on one side and all the initial momentums on the other side, it could have been the other way around as well, né? I could have said initial momentum of A plus initial momentum of B is equal to final momentum of A plus final momentum of B. Then I see if I add up all the momentums in the beginning of the two different bodies, that is going to be equal to the sum of all the momentums at the end. And that is called my law of conservation of linear momentum. The total linear momentum in a closed system remains constant. What is a closed system? A closed system is just an isolated system where no external force acts on it. Let me give you an example. If you have a ball that you throw on the ground, let's say the ball is the one body and the ground is the other body, that will not be a closed system because on the ball you have gravitational force acting. So there's an external force acting on one of the bodies on the system, so that is not an isolated system. Often in sums on momentum, you will see that they say ignore friction or view this as an isolated system. As soon as they talk about the isolated system, you know it's safe to use the law for conservation of linear momentum because that only applies in an isolated system. Okay, I can represent this with an equation. Oh, there's a small mistake. This must be a small p, capital P is for power, so give me a quick opportunity to just correct. That's much better. And I have the sum of the momentums before is equal to sum of the momentums after. These signs, the sum of all these mathematical operators, are extremely important in science. If you leave them out, you change the entire meaning and then they cannot award you any marks. If I leave out the sum of, then I say the momentum of something before a collision is equal to the momentum of something after the collision. Let's take that girl in our example. We clearly know her momentum before wasn't equal to her momentum after. If nothing else, at least the direction changed. So that is not true. The complete sum of the momentum of A and B is equal to the sum of the momentum of A and B afterwards. If I expand this formula, it looks like this. So any one of these two formulas you can write down in a sum. Okay, let's have a look at an example. A motor car with a mass of 300 kilograms travels at a velocity of 20 meters per second west, and then it hits a truck with a mass of 800 and a velocity of 25. Always in momentum sums, the first thing that I do is I choose a direction as positive. So I'm going to represent west is going to the right, and that's going to be positive. I like to draw this diagram for all my momentum sums. I usually have two bodies. Each of them have a velocity beforehand, and then I have two bodies afterwards, and each of them with velocity afterwards. The direction of the arrow usually for me represent the direction in which they're moving and remind me in which direction my signs must be. So if I take this diagram, there's usually two bodies, and then either they go apart or they explode or they have a collision or something happens or some kind of incident happens, and then I have the momentum afterwards. So let's look at our example here. If I look at my two masses, the two bodies that I'm talking about now is the car and the truck. So the car has a mass of 300, the truck has a mass of 800, and that's not going to change during the collision. Well, not in this case. Probably a little bit of bang up and so on. But anyway, if I have 300 kilograms over here, I'm going to have 300 kilograms over here. My truck is 800 kilograms over here and 800 kilograms on that side. Okay, so if I fill in all the values, my diagram starts looking like this. Initially, my car traveled at 20 meters per second west. That is what this information is saying. And the truck is with a mass of 800 is traveling at 25 meters per second west. Okay, so these are my two bodies. I can see my truck is coming from behind. It's going to have a greater mass. This is just a representation. This is not how the car is looking on the road. Okay, this is just my two bodies. Okay, then I have a collision. And then afterwards, they tell me, after the accident, the motor car continues with a velocity of 22 meters per second west. But I don't know what my velocity of my truck is. I have to go and calculate that. So I write down my equation. I prefer to write it down like this. And then I stuck in all my values, make sure that my directions, all of them are positive because all of them are going to the right. And if I calculate my final velocity, I'll also get a positive number, and therefore I know that this velocity must be to the west. Let's take another example. Anati and Ashley is moving together on ice. Then Ashley pushed Anati slightly, and she continues with a velocity of 11 meters per second to the right. And you have to calculate Ashley's velocity after he pushed Anati forward. So if I put down or show you in my diagram, oh yes, before I do anything, I have to choose a direction so that I get my symbols and my directions correct. I must say this is the single greatest mistake of all grade 12s. They forget to choose their directions and then often end up with a number that was supposed to be negative that becomes positive, and that loses them a lot of marks. Okay, so I chose my direction, and then I'm going to write down my diagram. I've got my two bodies. It's Ashley and Anati. They've got masses of 55 and 63. And there is a situation before and a situation after when the momentum changed. So initially, both of them were moving at the same velocity. So I write it like this. And afterwards, Anati continued with a velocity of 11, and I have to go and calculate Ashley's velocity. So I plug in all my numbers in my equation, and then when I calculate my final velocity, I find that it's a positive number, so I know this must be to the right as well. One final example. I have a wagon with a mass of 12 kilogram, and I have a mass piece here of 5 kilogram. As the wagon moves forward, the 5 kilogram drops, and then they continue to go. Initially, this sum looks very problematic because I have something moving up and down, and I have something moving from one side to the other. In linear momentum, we are only interested in the motion that's going in this plane. So as far as our sum is concerned, this 5 kilogram mass is stationary because in this plane, it has no velocity. So I choose to the right as positive, and then when I fill in my diagram, I have my 12 kilogram wagon that's moving at 2 meters per second to the right. This one, as far as left and right is concerned, it's standing still. It's only falling up and down. So this one has a velocity of 0. And then afterwards, they become one body. So each of them will have the same velocity. The wagon, which is 12, will have a velocity of v afterwards, which I don't know. And the velocity of the 5 kilogram will have a velocity of v afterwards, which I don't know. Oh, I see. When I translated this, Afrikaans is na. I forgot to put in after. But this na is just the Afrikaans for after. Okay, so if I complete there, I had it right in this one. I just didn't have it right in my sketch. Okay, if I plug in all the different values, it will look like that. Let me just wait for that PowerPoint tool to disappear. I plug in all the values and I calculate my mass afterwards. It's a positive number, so I know, not the mass afterwards, I calculate the velocity afterwards. It's a positive number, so I know it must go to the right. Okay, your turn. Do try these couple of momentum sums, and then we'll get back to you in the next video. Good luck.